Anybody? Freezing cold? Anybody go to the library for some free cookies? No? On Saturday, free cookies made by the Friends of the Library. I made some of those cookies. There was a sandwich board out in front of the library and some signs? No? Okay, next year, free cookies in the library on Saturday. Very good, homemade. All right, so today we're actually getting ready to start the next chapter. So I'm going to just summarize and go over a little bit of what I went over very quickly last time. And then we're going to launch into the next topic, which is non-Newtonian fluids. So let me summarize a little bit where we've been. We have spent a fair bit of time deriving the Navier-Stokes equations. And the Navier-Stokes equation is the microscopic momentum balance. So we ended up with this version, which has our friend, the stress tensor in it. The formal name of this tensor is the total stress tensor. And I don't say that because I actually don't deal with pi very much. I mostly, after today probably, will only be talking about tau, the extra stress tensor, which I'll just call the stress tensor. So during this portion, when it's all new to you, I have to try harder to call things by their complete formal names. This is the total stress tensor. And we asked the question last time what to do with it, and we split it into two parts. And this takes some getting used to, and so I'll repeat a little bit here, but we'll be dealing quite a bit with the extra stress tensor, tau, and the pieces of the total stress tensor. So we'll see this quite a bit. Now, there are two parts to the stress tensor, the isotropic stress and the rest. So the pressure is an isotropic stress. And as I pointed out, let me point that out even more clearly. You've heard of pressure. You've heard of pressure from, for instance, the ideal gas law, PV equals nRT. And this is the same pressure. If you've done any experiments in, say, fundamentals lab in ChemEng or in a fluid mechanics laboratory, you've put some kind of a meter, let's say, on a flowing fluid, perhaps, and measured a pressure. Okay, this would be a gauge pressure. And this is also this guy here. I'm going to point out when we get to it how I know for sure that this pressure that I measure, which is actually a stress here at the wall, how I know it's just a regular pressure, but I'll just tell you for now that it's just regular pressure. It's nothing exotic. It was a very simple concept when you first learned about it. Pressure is defined as force per unit area. And you went on with that. In the case of PV equals nRT, maybe you had some kind of a vessel and some pressure gauge, some pressure transducer measuring the pressure inside. And it didn't matter where the end of this pressure meter was. It doesn't matter inside that vessel because the pressure is everywhere the same inside that vessel. But we've made pressure more complicated because we're dealing with fluids that can exert forces in a lot of different directions, more than this type of pressure, which is isotropic. The type of pressure you've been dealing with up to now has always been just the kinds of shear stresses, or not shear stresses, just the kind of stresses in fluids that are isotropic, which means independent of direction and perpendicular. So independent of direction of surface means that the end of this probe, it doesn't matter which way it's pointing. It can be pointing left, right, up, or down. It's going to measure the same pressure. And it's orthogonal. It's perpendicular. So it matters what impinges on this surface perpendicular. It doesn't measure, the pressure transducers that maybe you've worked with don't measure stresses that are shear stresses. They only measure stresses that are perpendicular to the surface also. Those are the simplest types of stresses. So you maybe, I don't know if you noticed when you first heard the term stress, that it was also defined as force per unit area. Okay, it's also force per area. And I don't know if it ever struck you that why do we need a new word for force per area? Because we define pressure as force per area. And you're starting to find out why we need a different term for it. Is that this refers to a much more complicated thing than this. Okay? Stress is, by units, force per area. But by meaning, it's all this complicated stuff we're getting into. Okay? Pressure is actually this very, very easy corner of stress is pressure. And formally, it's what we're writing on this slide. That pressure is an isotropic force per area. It always acts normal to a surface. And using the math we've taken all this time to figure out, it's this scalar P multiplied by the identity tensor, which in Einstein notation is P times EJ, which if you write it out is P times E1 plus E2 plus E3. Or in matrix form, it's this diagonal tensor. So that pressure you can subtract from the total stress tensor and get the extra stress tensor, which, as I said, I'll be calling the stress tensor. And the stress tensor is the complicated thing that we need to figure out. Now, again, back on this slide, I glossed over the fact that these are molecular stresses. And that was true for this pressure that we talked about before. In intro chem class, they perhaps said, okay, you have a vessel and inside there's a pressure, it has a certain volume, there's a certain temperature, PV equals nRT, number of moles, ideal gas constant, absolute temperature. This pressure is a molecular force. There are little molecules pinging around, moving around inside this vessel, either if it's a liquid or a gas, there are these little molecules. And when you put some measuring device, let's say the end of a transducer, into this device, molecules hit it and bounce off. And that molecular motion is what gives rise to the force per unit area on this little surface. And usually this is a piezoelectric device that measures force. On that area, you divide by the area, and that gives the pressure. So these are molecular forces. And that's also what this extra stress tensor is. It's molecular forces. But it's all the molecular forces that are not the easy ones. Okay? So that's why it's going to take us the rest of this class, and in my case, the rest of my career, to study this guy right here, the extra stress tensor. Now, before we're now moving on to this how to study the extra stress tensor. But as you know, in the homework and this section, we talked about this stress tensor in the microscopic momentum balance. And in order to do that, we needed the relationship between that stress tensor and the velocity. And that is called the Constitutive Equation. And that's the meat of our discussion in rheology, is what is the relationship between velocity and stress in a moving fluid. For the Newtonian fluid, I just gave this to you very quickly at the end of class. This is the Newtonian Constitutive Equation. It's true for incompressible fluids. It was arrived at through experimental results. If you go back to chem class and pick up the kinetic theory of gases, you can also derive it if you're really very good at tensor mathematics. You can say I have molecules that interact, that just bounce and bounce off each other elastically. And if you assume elastic collisions of these gases and certain rules about how their speeds are related to their temperature, you can derive this tensor relationship for ideal gases. And then, as I said last time, if you take this tensor equation and put it in here, okay, actually, it's easier to put it in here. This, to get from here to here, we just need the definition of this tensor in terms of tau. And it's all just tensor algebra to get from here to here, and to get from here to the Navier-Stokes equation, this one. Just a bunch of tensor algebra, nothing exciting to get here. So the Navier-Stokes equation, which you've used before, is just the microscopic momentum balance. It says that the rate of increase of momentum in a control volume plus the net flux in is equal to the sum of the forces. And the forces on the control volume are isotropic pressure, viscous forces, and gravity body forces. Now, I also, back here, I skimmed over one slide where I talked about this stress tensor. And let's go back over that. We've arrived at the momentum balance, and we've defined the stress tensor, the extra stress tensor, and now we need to know what it is. The stress tensor is, take a look at this equation. Let me go back to the Navier-Stokes, or let's say this one, the Cauchy momentum equation. This is a set of three differential equations. It's got the 1, 2, and 3 component in Cartesian coordinates, or r theta z. But we've got this troublesome term. How can we possibly solve a problem that has that troublesome term in it? Now, you've just done some homework solving using this equation. And how did that work out? Well, it worked out that you did a steady flow, and if it was unidirectional, this went out. If it was the flow in a circle, it didn't. You would make some reasonable, either you would allow the equation to tell you about pressure, or you'd make reasonable assumptions about pressure. You knew things about the velocity. And so velocity appeared. Pressure, you had to know. Sometimes the equation told you what to do with pressure. Sometimes you had to make some assumptions about pressure. But at the end of the day, after whatever assumptions, you solved for the velocity field. By simplifying assumptions on the velocity and the pressure, you were able to solve for the velocity field. The equation in the derivation before this has the same left-hand side, but it has that extra stress tensor. It has this term with the extra stress tensor. Now, how would we possibly solve this equation? Well, we'll still know things like steady state, maybe, and unidirectional flow, or somehow to simplify that. We can still handle pressure the same way, but we can't simplify this until we know how the stress is related to velocity. Okay. If we know stress is a function of velocity, we can plug it in and march down our merry path. If the merry path is a very difficult differential equation, then we go take extra classes in that, or go find ourselves a computer program. Everything is fine. And that, in fact, is the case. But the missing piece of information is this. Okay? But what is this? And that's the problem. Okay? Where did it come from? It came from saying that the sum of the forces on our control volume, on our arbitrary volume, had to be molecular forces and gravity. So we put it in there because we knew that there would be molecular forces, stretchy molecules or or particles rubbing past each other. We know there are molecular forces. But in fact, all we've done so far is sweep all of our ignorance about those molecular forces into this mathematical expression. It makes us look like we know more than we actually do. Okay? Until we know this functional form, all we've done is call it something. Now, we've called it something mathematically handy because we know that this entity somehow is related to force per unit area in a fluid at a point. There's an isotropic component and there's an anisotropic component, and this is the anisotropic component. We know that because of how it arrived at the equation, but we don't know anything about how it's related to the fluid motion. We have to start over in some sense to figure out how it's related to the fluid motion. It's a big problem. It's a big, thick book problem, okay, to get to what this equation is. So now we're setting down on that path. For the rest of the course, we'll answer that question. What is this? That's the main task for this now. So this is called the constitutive equation. That's just a name. Formally, perhaps I could call it the stress constitutive equation. The word constitutive refers to, like the word constitute, okay? And it relates to the fact that there are material properties that are somehow embedded in that equation. And they constitute the meaning of this equation. So we need to know something about materials in order to answer a question like this, because we need an equation that tells us how the material is constituted, how sometimes people do say constitutive equations. The one constitutive equation we know is the Newtonian. The Newtonian one is tau equals minus mu gamma dot, which is minus mu del V plus del V transpose. It's a very simple one, and you've had a little bit of practice working with it. How did Newton come up with such a thing? Well, actually, he didn't. Newton came up with Newton's law of viscosity. Newton came up with the 1D version. Tau 2,1 equals minus mu dv1 dx2. And that one, I think we can understand how maybe he came up with that. You know, you say you put a very, very simple flow, flow between two parallel plates. You put a fluid in the middle. You move the top plate at a constant velocity. It turns out that if you do that at a slow enough velocity, you get a very reasonable organized flow. And the total force per area on the top plate, turns out to be proportional to the velocity divided by the gap. And that's the same thing as this equation. Force per area is proportional to velocity divided by the gap. That's how he did it. It's good science. And he figured out how that there should be some simple proportionality constant between this velocity gradient and this stress. The people who figured out that this simple scalar equation is really in 3 dimensions and for all flows, not just this simple flow. In 3 dimensions and for all flows, it's equal to this tensor equation. They were more mathematically inclined. And they had the tall shoulders of Newton and Leibniz and all the great mathematicians to stand on to get from here to here. Their approach was something like how we're going to approach it. We're going to ask sort of mathematical questions about the equations to sort out what what mathematical rules have to be held by these equations in order for them to make sense. And we're going to track down sort of what are the mathematical implications of this one, which seems to work, and how are its predictions different from what we see plastics and other interesting materials doing. So we're going to compare what simple materials do and what complicated materials do. And we're going to compare what simple equations and complicated equations do. And we're going to try to sort it all out. So the starting point will be the Cauchy momentum equation, which is the momentum balance, which is correct for all fluids. And we're going to concentrate on how to get information about the mystery term for materials that do not follow the Newtonian constitutive equation. Okay. Very vague, perhaps. Let me be more concrete. This constitutive equation, the Newtonian one, the beauty of this is that it is true for all flow situations. Going back one page, for Newtonian fluids, I know this. Because I know this, I can plug it in here. I get the Navier-Stokes. And if I have a sufficiently powerful computer program, I can solve this for any flow situation. I've asserted to you that for complicated flow situations, there are materials that behave strangely, and you've seen a videotape of some strange materials. So when you have materials behaving strangely, I think our intuition is rather than jump into a complicated mathematical model, you want to take a look at how that strange material is behaving and kind of get it organized. Well, let's do the same thing to 5 different materials, or let's do them at 5 different rates. Let's do some very simple test to see how these materials might be a little different. And that's actually also how rheology organizes itself. So our next chapter is called Standard Flows. And what it is a description of these very simple flow situations. And there are 2. One is shear, and the other is elongation. What are these very simple flow situations that we can define so that we can put complicated materials into those circumstances, into those flows, and make them sort themselves out, make them behave so that we can see how they're different from, say, how water and oil and other Newtonian fluids behave. So our next chapter is about what kind of standardized tests we're using. You could think of it like ASTM, if you've heard of ASTM standard tests. But you know what? The reason there are so many ASTM tests, if you have any experience from your co-ops or something on ASTM tests, the reason there are so many rules to an ASTM test, this size material in this size dye at this size rate at this prescribed temperature, everything is prescribed. And the reason is that the natural world is so complicated. If you use a different shaped dye made out of a different material and went at a different speed, you'd get a different result. So you need to hold everything constant and compare apples with apples. In rheology, we want to compare apples to apples also. So we have that same driving force as the standardized tests, but it's worse than that. We want to be able to take the results from one test and use them to predict every other flow possible. Okay, we're trying to figure out the constitutive equation. If the constitutive equation is correct, we can predict every flow. There's no ASTM test that even thinks of suggesting that. ASTM tests are tests invented by engineers to at least get something the same. Okay, so that if I buy polyethylene from Dow, and Dow doubles the price, and I want to turn around and buy polyethylene from DuPont, but I want it to behave the same. I want it to do the same thing that the one I was buying from Dow does. How do I compare them? Well, you invent a bunch of tests, and you say, well, when I take my Dow material, and I take 6 grams of it, and I put it in a vessel shaped like this, and I put a 10-pound weight on it, it flows out at this temperature, it flows out at this rate. That's a standardized test, melt flow index. Okay? It's a standardized test. And you tell DuPont, I'll buy from you if you can get me a material that will do this same thing. Okay? And that's how engineering is done. And that's how metals are done as well. All these ASTM tests are just tests that have been figured out to try, basically, to allow equivalent materials to be selected for different devices. That, it turns out, and engineers know this too, they're not always right. You can get 2 materials, one from Dow, one from DuPont. You can match all the specs. Maybe there's even 30 specs. They just keep adding new ones trying to make this not happen, and it keeps happening. They'll match all the specs, and they won't work the same. And the reason it won't work the same is because they really don't know exactly what is going on. They just picked tests. And the tests were selected not stupidly, but not perfectly. We're trying to do something so much harder. We're trying to pick tests that will elucidate the behavior of a material in such a complete way that when we're done, we will have an equation that will tell us how it will perform in every circumstance, always. That's the constitutive equation. The constitutive equation, once you have it, you can put it into the momentum balance, and you can predict any flow. So it's a very big task that we're biting off. And it's not possible. But it is possible to make progress, and that's as far as we're going to get. We're going to talk about the standardized tests and why we pick them. So nobody really talks much about an ASTM test, why they pick it. It picks it because it works well enough for some circumstance, and that's really all the justification you need. We need to justify them because we are going to try to take the results of these tests and use them to design the constitutive equations, reject certain constitutive equations, and hone in on the correct mathematical forms that they must be in order for the equations to be correct. All right? So we're going to start by talking about these 2 standardized flows and all the different subclasses of these flows, and then why we pick them. Then in the next chapter, we're going to talk about, well, what happens? What happens when you put various materials into these flows? What kind of behaviors do you see? And we're going to talk about those. And we have to store up some knowledge about how polymer materials really behave. And then we're going to talk about the constitutive equations themselves, because the behavior and the tests are going to eliminate whole classes of equations as possibilities for the constitutive equations. For example, one I can talk about right now is the symmetry of the stress tensor. Okay. The only constitutive equation we know so far is the Newtonian, which is tau equals minus mu del V plus del V transpose. And this constitutive equation follows one of the important rules of stress, which is that we haven't talked about it too much, but the stress tensor is always symmetric. So that means tau is equal to its transpose. And if you check me, if you take the transpose of this, you'll find that it's equal to itself. You can sort of see why, right? This one becomes transposed, this one becomes untransposed, and it becomes the same equation. This rule comes from conservation of angular momentum. conservation of angular momentum. So we're going to be looking at laws and observations that form constraints on constitutive equations. So I'll summarize that by saying we're now going to talk about polymer behavior in standard tests and use that to narrow down, let's say, the possibilities of constitutive equations. All right, so let's begin. I forget what chapter it is. The standardized flows. We've been talking about Newtonian fluids. Now we'll talk about non-Newtonian fluids. The definition of a non-Newtonian fluid is any fluid that does not follow the Newtonian constitutive equation. So anything that's not Newtonian is non-Newtonian. But now we want to get specific about what does that mean? How does it not follow? And so we're going to use some standard tests, and I've shown two types of standard tests on this slide. This is a shear type test, and this is an elongational test. This looks like an Instron tensile tester, and this looks a little bit like a Brookfield viscometer. I don't know if you're familiar with either of those. So we'll start with shear flow and be very formal about it. Okay, we're going to define two testing flows. One is called shear flow, and this is the definition of shear flow. Shear flow is this flow that Newton used. We take two very long, very wide plates. We put our test sample in between. Now, we're making this flow as simple as possible because we don't want to assume anything about its material behavior. We can't assume it's Newtonian, for instance, because that would be against the whole point. We want to make a measurement that does not assume the constitutive equation. So we're just going to put an unknown fluid, peanut butter or polyethylene, between two plates. We're going to move the top plate at a constant velocity. So for a standard flow, we're changing our point of view. Up till now, we've been solving for the velocity field. Now we're not solving for the velocity field. This is going into the lab and making this velocity field happen. So this is the velocity field we will impose on our sample. We will impose a velocity field that has V2 and V3 0. So the flow is only in the one direction. And that flow will vary in the two. So we will make it a linear velocity profile. We're not going to solve for it. We're going to say it must be produced like that. This is a flow where layers of fluid slide over each other, and this is the particle path line. If you have a fluid particle at this point, sometime later it's going to be in the same plane, a little bit downfield. At different values of x2, it moves down different amounts, and that's the shearing action. Shear is a natural choice because shearing actually occurs even in complex geometries. Shearing always occurs near walls. So if I zoom in on the wall, then because of the no-slip boundary condition at the wall here, just a little bit away from the wall, the material is moving, and so there's a simple shear flow going on very close to the wall. This is done in the lab by actually trying to get two plates to slide past each other, but there have been other clever ways that this has been produced. It's a little hard to keep this steady, So you can put two samples in between two plates. That's the double parallel plate. You can do this geometry that we just did in the homework, which is called couette flow, where you have something turning in the center, or you could actually turn the cup if you like, instead of turning the bob in the center. And in this narrow region here, a shear flow appears. In the book, I talk about this flow, parallel plate flow. That's another very common shear geometry. And then a modification of the couette geometry that produces more torque is the double-walled couette. So this one, as it turns, will produce more torque because there's fluid on both sides. And so for a low viscosity fluid, that produces a higher signal. In shear flow, we have a standard convention, which is 1 is the flow direction, 2 is the gradient direction, the direction in which it varies, and the third direction, where nothing happens, is called the neutral direction. We've already used this convention back here when we defined the velocity field in shear flow. So the 1 direction is the direction of flow, the 2 direction is the gradient direction, and there's nothing going on in the 3. Shear is a standard flow because it's simple. It represents all sliding flows, like those flows that happen near the wall. And it has a simple stress tensor. Okay, now that's an interesting assertion that I've made. I said that the shear has a very simple velocity field. Well, that's by definition. I defined the flow by its velocity field. But I've also said it has a very simple stress tensor. And this is less easy to talk about, but it's nevertheless important. Because again, I don't want to say what the stress tensor is. I don't want to say what the constitutive equation is, because I need this to be useful no matter what fluid I put inside my test device. And the next thing I'd like to discuss is how I know that the stress tensor is simple for this flow. Okay. This is a simple flow. Actually, this is about the deformation. Let's see. I guess I'm going to talk about that at the end. I'll talk about at the end how I know that the stress tensor is simple. I want to contrast this flow with elongational flow, which is the other standard flow. And I can do that by looking at the actual deformation that takes place in a shear flow. And the details of this derivation are in the book. I'll just indicate them briefly because I think it's a little bit hard to follow in lecture format. But if you look at two particles in a shear flow that are separated by a certain length initially, sometime later, those particles will sweep downstream, but they will get far apart by this hypotenuse amount. They started off just L0 apart. They were in two different planes. And when they swept downstream, they are now this distance L apart. You can do the geometry, and it turns out that L is proportional to the time. So the longer you shear, it makes sense. This line just gets longer and longer. The longer you shear, the further apart the two particles get, linearly with time. So let's remember that for the moment, because we're going to contrast that with our other standard flow, which is going to be quite a bit different. So we have shear flow, and our other flow is going to be elongational or extensional. Same thing. Shear flow, particles separate linearly with time. And it's a sliding flow. The second standard flow is elongational flow, which is this stretching flow, this stretching and thinning type flow. We're going to describe it mathematically the same way we described shear flow, so let's remind ourselves quickly. we define shear flow by giving the velocity field mathematically, sketching the velocity field, and sketching the particle path lines. So now we'll do the same for elongational flow. This is the details of that linear calculation. I'm going to skip that. For elongational flow, this is the sketch of the velocity field. This is the velocity field written down in mathematical form. Okay? It's much more complicated. Let me see if I can explain it to you. If I start with a sample that's the shape of this pen, and I stretch it, if I elongate, then in one direction, the particles are getting separated. And in the other two directions, the particles are coming in. All right, so that's what this is showing. In the 3 direction, which is the flow direction in elongational flow, the particles are separating. And in a 1-2 plane, the particles are coming in 2 directions. And in fact, this is a cylindrically symmetric flow. They're coming in at all angles. So it's coming in the 1 and 2 directions. It's extending in the 3. So that's what we have here. This is a positive term. This is the velocity in the 3 direction is positive. In the 1 and 2 directions, the velocity is negative. It's coming inward. There's some sort of a mass balance there, which we haven't talked about yet, but it must be the case that this extends and these two both contract at half the rate due to the mass balance. So I said we talked about shear flow. We drew the velocity field. That's all of this is the velocity field, but we also drew the particle path lines. These are the particle path lines. So in a 1-3 plane or a 2-3 plane, these are the particle path lines. And in the 1-2 plane, they're just particle paths are just coming straight in. Now, this is a very complicated looking flow, although it's maybe understandable to you because it makes sense to include a kind of a stretching flow. But unfortunately, we were not able to define a very simple, one-dimensional stretching flow. Nothing that looked nearly as simple as shear flow with one velocity component. We needed 3. We needed to stretch and then have the flow contract in the other direction. So elongational flow is naturally more complicated than shear flow. It's more complicated and it's also very severe. Now, why would we pick it? We pick it because it happens all the time. When you're not near the walls you have shear flow, but when you're not near the walls, there's extension happening all the time. So for instance, flow through an orifice, if you look at a piece of fluid flowing through here, it is being stretched in some flow direction. If you zoom in on this piece of the fluid as it exits, say, a capillary dye, it's exactly going through that elongational flow. It's being stretched in one direction, and it's coming in the other. So you can show, again, if you're very mathematical, you can show that all the deformations that a material undergoes in a complex three-dimensional flow can be split into these 2 flow classes: sliding and elongating. Okay? Simple shear flow and simple elongational flow. And so from a rigorous point of view, that makes these 2 choices very, very attractive, because as long as we can get the right combination, we're capturing all the types of behavior that the fluid might have. How do we produce this flow in the laboratory? Very difficult. The Instron tensile tester does not do this flow. The Instron tensile tester, you can put a cylindrical piece of a metal or a plastic into an Instron tensile tester, and you can move them apart. But to move them apart according to the velocity field that we just picked, I'm going to show in a second, you must move them apart exponentially fast. The instron tensile tensor grabs onto two ends of a polymer and holds onto them and doesn't let them deform. And we need those ends to deform just as much as everything else is deforming. So ways that people have tried to produce this flow are to, this is a very simple test that's done with very low viscosity fluids. It's like taking a sample between your fingers and stretching them apart. It has the same downside as the instron tensile tester in that the edges do not deform the same way as the middle. So here in the middle, the fluid is deforming something like our elongational flow, and clearly at the edges it didn't flow inward. So people have been clever and produced devices like this where they take rollers, put a sample in the middle, and roll the edges in such a way that to pull it out. And that does a better job of producing the flow we're talking about. This opposing nozzle device applies suction on these ends and also tries to produce that flow. That's an interesting flow people have used. And in some devices, they produce this flow in reverse. So we move these plates together in such a way that it produces an elongational flow in reverse. So this flow seems like a lot of trouble, so why have we picked it? It really is a simple velocity field. It's the simplest one we could pick. We need a way to represent stretching flows, and it will turn out that this one also will have a simple stress tensor. So if we look on this list, it represents stretching flows. And it also represents particles that are severely deformed. As I'll talk about next, particles in elongational flow separate exponentially. So this is my next topic. I'm going to show next time that in elongational flow, the particles separate exponentially with time. And I've already discussed that this is a sliding flow and this is a stretching flow. And there'll be a third topic that we'll talk about next time, which is the nature of the stress tensor. The nature of the stress tensor is very important because we're now in a circumstance where we need to measure the stress tensor. And to measure things, we want things to be as simple as possible. Both of these are simple flows. Okay, so I'll continue that discussion next time. Finish on time today.